In this module, we will explore how the behavior of solvents and solutes in real solutions deviates from ideal behavior and how it can be described thermodynamically. When we move beyond ideal liquid mixtures and ideal dilute solutions, we encounter the need for techniques to describe real solutions thermodynamically. The concept of ideality serves as a valuable starting point. It allows us to derive useful limiting laws. However, it is only an approximation. In general, to account for deviations from ideal behavior, the form of the expressions used for ideal systems is retained, but their interpretation is adjusted to include effective values rather than actual values. Such adjustment is a universal approach in thermodynamics. It extends the applicability of idealized equations to real systems. In this quest to establish a thermodynamic description of real solutions, we will make use of the following expression that I have already introduced previously. Mu IL equals mu IL asterisk plus RT times the natural logarithm of the ratio of Pi over Pi asterisk. Here, mu IL represents the chemical potential of component I in the solution, while mu IL asterisk is the chemical potential of component I in its pure liquid state. The term Pi asterisk denotes the saturation vapor pressure of the pure liquid I, and Pi is the pressure of the vapor of the component I that is in equilibrium with the solution. This expression is based on the equilibrium established between a solution component and its vapor. Importantly, it holds for any type of solution, whether ideal or real. Moreover, it serves as a bridge between the theoretical thermodynamic properties and experimentally observable physical characteristics of solutions. When considering the chemical potential of a solvent, we start by examining its ideal behavior. In the ideal case, the chemical potential of the solvent in the solution is given by the following equation. Mu Al equals mu Al asterisk plus RT times the natural logarithm of Xa. Here, Xa is the mole fraction of the solvent. For non-ideal solutions, we preserve the mathematical form of this relationship, but replace the mole fraction Xa with the activity Aa. The chemical potential of the solvent in a real solution is then expressed as mu Al equals mu Al asterisk plus RT times the natural logarithm of Aa. By doing so, we retain the same mathematical structure of the formula for the chemical potential for both ideal and non-ideal solutions. The dimensionless activity of the solvent Aa can be thought of as an effective mole fraction. It accounts for deviations from ideality caused by non-ideal interactions in the solution. Now we recall the first equation and use it to connect the chemical potential of the solvent in a solution with its vapor pressure. Remember that this relation holds true for both ideal and real solutions. Using two previous equations, we can establish a connection between the activity of the solvent and its vapor pressure. AA equals PA divided by PA asterisk. This equation exposes the nature of activity of a solvent as a quantity that can be determined experimentally by simply measuring the vapor pressure of the solvent in its pure state and in the solution and applying this equation. Here we can also recall that the more dilute a real solution becomes, the better the behavior of the solvent aligns with the ideal behavior described by Raoult's law. This means that as the mole fraction of the solvent approaches 1, the activity of the solvent approaches the value of the mole fraction. To quantify the deviation of a real system from ideal behavior, we introduce the activity coefficient, gamma A, as a ratio of solvent's activity and its mole fraction. The more dilute a real solution becomes, the closer the activity of the solvent becomes to the value of its mole fraction. Therefore, as the mole fraction of the solvent approaches 1, the activity coefficient of the solvent approaches 1. The chemical potential of the solvent in a real solution can then be expressed using the activity coefficient as mu Al equals mu Al asterisk plus RT times the natural logarithm of XA plus RT times the natural logarithm of gamma A. In this equation, first two terms on the right-hand side correspond to the chemical potential of the solvent in an ideal solution. This equation highlights the fact that the activity coefficient captures all non-ideality of the solvent's state in a real solution. It also indicates that the standard state of the solvent is defined as its state under the total external pressure of 1 bar, with the mole fraction of the solvent equal to 1, corresponding to a pure solvent, and with the activity coefficient equal to 1. Given that the purer the solvent, the closer its behavior to the ideal one, the last condition is fulfilled for the pure solvent automatically. When we consider solutes in a solution, the situation becomes more complex. Unlike the solvent, the ideal behavior of a solute is described by Henry's law. The key challenge in defining activity, activity coefficients, and standard states for solutes arises from this fundamental difference in behavior. Unlike solvents, solutes approach ideal dilute behavior as their mole fraction in the solution approaches 0 rather than the pure state. Let us now consider a more detailed thermodynamic treatment of the solute in an ideal dilute solution. For an ideal dilute solution, the relationship between the mole fraction of the solute and its vapor pressure above the solution follows Henry's law, Pb equals Kh times Xb. Kh is Henry's law constant, which depends on both the solute and the solvent. The chemical potential of the solute in the gas phase can be expressed as mu Bg equals mu Bg standard plus RT times the natural logarithm of the ratio of Pb over P standard. Combining it with Henry's law, we obtain the following expression for the chemical potential of the solute in the gas phase. Mu Bg equals mu Bg standard plus RT times the natural logarithm of the ratio Kh over P standard plus RT times the natural logarithm of xb, which in turn equals the chemical potential of the solute in the solution. We can combine the first two terms in the expression for the chemical potential of a solute in a solution and introduce a new standard chemical potential of the solute. Mu Bl standard equals mu Bg standard plus RT times the natural logarithm of the ratio Kh over P standard. The expression for the chemical potential of a solute in an ideal dilute solution as a function of its mole fraction thus becomes mu Bl equals mu Bl standard plus RT times the natural logarithm of xb. This new standard chemical potential corresponds to a new standard state specific to the solute in an ideal dilute solution. Formally, this standard state is a hypothetical state where the solute is infinitely diluted and its mole fraction equals 1. Of course, such a state is purely theoretical and cannot exist in reality. However, the fact that such a state cannot exist is not relevant. It is actually nothing more than an extrapolation of Henry's law to a solute mole fraction of 1. Such an extrapolation would, for example, imply that the pure solute would have a vapor pressure equal to the Henry's law constant, rather than to its actual saturation vapor pressure. This extrapolated standard state is used even for solutes that cannot exist as pure liquids under the given conditions, such as dissolved gases. For example, oxygen dissolved in water at room temperature can be described thermodynamically, even though liquid oxygen does not exist at these conditions. This seemingly peculiar definition of the standard state ensures that the chemical potential of any solute can be systematically described using thermodynamic instruments, regardless of where the solute exists as a pure liquid or only as a solute in a solution. Solutes in real solutions deviate from ideal dilute Henry's law behavior. To account for these deviations, we introduce the activity AB in place of the mole fraction xb, similar to the approach used for the solvent. This adjustment leads to the following expression for the chemical potential of the solute. Here, the activity of the solute is an effective value of the mole fraction of the solute that satisfies the Henry's law. It means that this effective value, the activity, is given by the ratio of the partial pressure of the solute in equilibrium with the solution to the Henry's law constant. The standard state of the solute remains unchanged. This indicates that all deviations from ideality are captured in the activity. To quantify deviations from ideal dilute behavior, it is sensible to introduce the activity coefficient for the solute. It is the ratio of solute's activity to its mole fraction. Substituting the expression for the activity into the equation for the chemical potential of the solute, we obtain the following expression. Similar to the solvent, the first two terms correspond to the chemical potential in the ideal case, while the activity coefficient captures all non-ideality in the solute's behavior. Now, when does the behavior of the solute in a real solution approach ideality? As the mole fraction of the solute approaches zero, which corresponds to an infinitely dilute solution, the solute obeys Henry's law. This means the activity AB converges to the mole fraction XB, and the activity coefficient gamma B approaches 1. In this limit, the deviations of solute's behavior from ideality disappear.